as well. The next talk is from Professor Linda Nazar, who is at the University of Waterloo, Ontario, Canada, where she's chemistry professor, senior Canada Research Chair in solid-state energy materials, and distinguished research professor. Professor Nazar is known for her research in electrochemical energy storage, with topics that span lithium-ion batteries beyond lithium-ion and solid-state ionics. And the floor is yours, Linda. Please go ahead.
Well, thank you, John, and thank you everyone for attending. Can you all hear me well? It says I have a poor call quality. But anyway, I'll just proceed ahead. So I want to thank Wiley and Yunhui Huang, of course, John, for organizing this great event, and especially for John for having a birthday, and also acknowledge the 10th anniversary of Advanced Energy Materials. So my talk has changed a little from the original title. I'm going to be talking about all solid-state batteries, and hang on a second. So I'm going to be talking about all solid-state lithium-sulfur batteries most specifically, and advanced functional materials. And Wiley suggested I do this in light of a paper that we just had accepted in the journal, whose title is shown here. So this is what's sort of the inspiration for my talk today. You can find the paper online, I think, very soon. And so I especially want to mark this occasion by wishing John a very happy birthday. I'm one of your biggest admirers, John, and I have been for decades, literally decades. And so a very happy 98th birthday, and I wish you great health, lots of laughs in the years to come. And I look forward to attending your 100th birthday celebration in a couple of years. So there's a lot of, I think, interest in solid-state batteries in general, perhaps not so much, sorry, I'm switching slides here, not so much in lithium-sulfur batteries, although they have been a matter of interest. And most of these batteries consist of effectively sulfur, a solid-state electrolyte of some sort, and carbon. And this is typically something like Li3PS4. And what's pretty surprising is that in the solid state, you can actually trigger the conversion from sulfur to Li2S, which is reversible. And of course, the advantage is that this prevents the dissolution and shuttling of lithium polysulfides, which are really problematic in liquid lithium sulfur cells. So this, I seem to be in a timing here, sorry. So there's other problems with these systems. With solid-state batteries, such as lithium limited ion diffusion, interfacial resistance at all of these interfaces, growth of lithium dendrites because they need a lithium metal anode, but I'm not going to have time to talk about those today. I'm going to be talking more about cathode challenges. And those include low active material content, often reports less than 25% weight of sulfur, 20 to 25, and of course, the real problem of co-oxidation of the solid-state electrolyte during cycling. And this is because the carbon is intimately interwoven with the solid-state electrolyte, and that wires the solid-state electrolyte thiophosphate, which are typically used in these cells, and thus causes oxidation. And that in turn results in very low initial coulombic efficiency of often in the order of 80%. And the low active material content results in low areal capacity. And a lot of these concepts have been reviewed, these challenges have been reviewed by Sun in a recent article in Chemical Society Reviews. So moving beyond carbon, there has been little work. I think some excellent work has been done by Stefano Passerini and Yuichi Ihara, which was published in Advanced Energy Materials a couple of years ago, where they use metal dichalcogenides as a host material, and specifically a combination of carbon FeS2. And the carbon is partly needed here because of the rather low conductivity of the iron disulfide. And their data is shown here. This is on the first cycle in black, and you can see there's quite a lot of irreversible capacity, so there's low coulombic efficiency, but then this mediates after about the fifth cycle. And they achieve fairly stable capacity cycling over 20 cycles. So their composites were prepared with a combination of carbon and iron disulfide and sulfur in a 4:3:3 ratio. So they have a low sulfur content. And they used a solid electrolyte, which is effectively a amorphous Li3PS4 combined with lithium iodide. The material itself is completely glassy. And as I said, they achieved a capacity of about 1,200 milliamp hours per gram, but a fairly intermediate to low loading of about 1 milligram per square centimeter. And of course, there's also a contribution from the FES2, and they were able to achieve around 3.55 milliamp hours per gram for these material loadings. So we decided to try a different tactic, which is to use a metallic disulfide. And our material of choice was vanadium disulfide. So it has comparable electronic conductivity to graphene on the order of 3,000 Siemens per centimeter. So it's really truly metallic. It also exhibits fast ion diffusion with a low migration energy barrier of about 0.22 volts. This is reported in these papers cited down below. And particularly interesting is that it's redox active within this lithium-sulfur window, so therefore it provides extra capacity. And one can compare these materials as these nanoflakes, as shown here with appropriate diffraction pattern on the right. Sorry, I'm having a bit of trouble with it. There we are. Advancing slides. So these, we call these nanoflowers, have basal dimensions in the order of 10 microns that are very, very thin layers of VS2. And these can be easily mixed with sulfur just by a traditional melt technique at 160, 12 hours to produce these composites. So critical here is that we form a sulfur VS2 core shell structure. So in other words, the metallic VS2 is completely coated by the sulfur, and the lithium thiophosphate, the Li3PS4, then incorporates on the outside of the sulfur. So it's not in direct contact with the VS2 metallic sheaths that perform the wiring for the system. So of course there have to be little gaps in between. This isn't exactly a perfect diagram, but this is the concept of this core shell structure. Minimizes contact between the metallic VS2 and the Li3PS4, thus mitigating the oxidation of the solid state electrolyte thiophosphate. And this just shows the good homogeneity of the system that we achieved. And this is sort of the concept here, where we have these highways of VS2 providing electrons to the system, but also providing lithium ions to the matrix of the sulfur, which is shown here in yellow. And the matrix of the solid state electrolyte then serves as a conduit for the lithium ions in this complex structure. And then we use lithium thiophosphate as our solid electrolyte, at least in these initial studies. So the first thing that we noticed was that the CV shows only two redox peaks, cathodic and anodic redox peaks, suggesting that the redox potentials that we're seeing in the system are at least overlapped. So we don't see separate potentials for the sulfur to Li2S redox compared to the intercalation of lithium and VS2. And so we have very smooth features in the solid state battery itself. You can see really just a smooth discharge and charge profile for this combination. So at the top of charge, all of the X-ray diffraction data shown here on the right suggested we have a combination of sulfur and VS2, whereas on discharge, on full discharge, we have a combination of LiS2 from the reduction of the sulfur and LiVS2 from exchange of the lithium incorporation of the lithium into the VS2 layer. And so these diffraction point patterns taken at point A, B, and C, D and E, all correspond to these points in the profile on the left. So point A is just the starting material where you can see the VS2. The sulfur is a little hard to see here because it's pretty much ball milled. And point B is partway through discharge, and you can start to see these VS2 peaks shift until finally at point C at full discharge, clearly they are indicative of LiVS2. And we concomitantly form the Li2S, which is indicated by the yellow triangle. So the reaction mechanism is then shown here on the right. And on charge, we simply repeat the process. The Li2S reacts with LiVS2 to form sulfur and VS2. So at the top of charge, we end up with the starting materials of the VS2, which is shown in the asterisks. The Li3PS4 peaks that you see here are simply because we had trouble actually peeling off the cathode layer from the separator in this particular diffraction pattern. And so this is just a residual separator that's showing up in the diffraction pattern. It's not from the reaction. So the take-home message here is that we have simultaneous conversion and deintercalation of sulfur and VS2 in this system. And so this is shown schematically here. In other words, in summary, the Li3VS2 provides lithium ions for the redox reaction. The VS2 provides the electronic pathway, and the LiXVS2 that forms midway is a mixed ionic electronic conductor. I think this is really very well known for most of you in the audience. And so this provides yet an additional ion pathway for sulfur reduction. So the overall reaction can be described as the following. So the proof is always in the pudding. And in this case, the pudding is the battery data. So we have here the discharge and charge profiles for the solid state battery. You can see that even on the first charge, we have excellent sulfur utilization. So we have a coulombic efficiency of 96%. And of course, this isn't, we're not at, lithium ion type qualities here, but this is for a solid state lithium sulfur cell, very, very good compared to the usual values of about 80%. And the sulfur utilization that we see in the cell is 85% as calculated from the amount of capacity that we see in this cell. And the system is pretty stable on cycling. You can see that we initially have an increase in capacity, which we sometimes call creep, and then it is reasonably stable over 50 cycles. And this is just showing the coulombic efficiency here on the right axis. And we've also investigated the rate performance of the system, where we switched from C over to 5 to C over 10. So this is the C over 5 data, the C over 10 data. We have the current density, and we've cycled the cell for about 200 cycles over this period of time. It still exhibits very good cycling performance. And this is the total loading in the system. And this is actually cycled with a metallic lithium anode. So the previous data that I showed you was against the lithium-indium alloy, but this proves that this indicates that the Li3PS4 is relatively stable against the lithium metal anode. It forms a passivation layer effectively at that interface of Li2S and Li3P, which then further stabilizes the system. So we're also able to create or fabricate fairly high loading cells that are shown here. So we have, this is the data for 7.7 milligrams per square centimeter and all the way up to 15.5. And of course, this started when we really increased loading of the cell. This is of the sulfur and the VS2. Ultimately, we start to run into problems with insulating sulfur, effectively impacting that capacity. So this is a bit of a challenge. I think that we still really haven't optimized the architecture of the cell, but this is our initial steps. We have reasonably good cycling efficiency, reasonably good coulombic efficiency and reasonably good cycling performance, at least in these initial stages. This is just literally our data. So we're still fighting with, of course, the issue of trying to increase current density in the systems while mitigating lithium dendrite formation. Another issue is that we have not really tackled the problem of expansion contraction as we undergo the Li2S to sulfur conversion reaction. It's a very large change in volume. And we were in the process of looking at adding binders to the cathode material before we went into shutdown. So we're revisiting that now. And of course, there's also then the concept of lengthening of when you build thick electrodes, you have a lengthened ionic electronic pathway. So we need more conductive solid electrolytes. And I'll just finish off the talk on a couple of these to address a couple of these points. So we've been investigating Argyrodite recently, and this shows the Argyrodite structure, showing these Frank-Caspar polyhedra within this cubic structure comprised of the PS4 tetrahedra. So these Frank-Caspar polyhedra cages contain these lithium clusters, and within these lithium clusters, there are different types of transport mechanisms for lithium ions. So there is what is called a doublet jump between the so-called 48H positions and the 24G, which lies in the intermediate space between the doublet. And there's also the intra-cage jump and the inter-cage jump. And the inter-cage jump is thought to dominate the long-range transport. So these materials have been studied extensively. A lot of these studies are shown here. And the best thing about Argyrodites is that they also appear to form a fairly good interface with lithium metal, as shown by Jürgen Janik, with these being the items that form the passivating interface. So the point here is that, that there are two different positions for the anion, which is either sulfide or the halide, for example, chlorine or bromine. And these are the 4C positions and the 4A position. So for the chlorine and the bromine Argyrodites, these are completely disordered. The sulfur and the halide are completely disordered over both of these sites. Whereas in the case of the iodine, it is completely ordered. And this results in very low conductivity. So this is just shows moving from chlorine to iodine, the extent of this disorder. So it's very high for chlorine, it's intermediate for bromine, and for iodine, it's literally 0. So there's no site disorder. And that correlates, as I said, with very low conductivity in the order of 10 to the minus 6 Siemens per centimeter. So it's extremely low. And now it turns out that halide-rich compositions have higher diffusivity. This is reported in a paper in JACS. We've been looking at halide-rich compositions reported here in this paper of Angavanti, and we're able to get ultra-high lithium-ion diffusivity, 10 orders of magnitude that of the lithium-germanium phosphosulfide, but I won't have time to talk about that. And I'll just mention our work on the Argyrodite iodides, where we effectively, by introducing antimony into the lattice, substituting, so these are antimony, silicon substituted antimony Argyrodites. So we've taken the conductivity from very low values, shown here, all the way up to 10 millisiemens, and in fact above. And you can see that in this plot that as the conductivity increases, the activation energy drops as expected. And this increases with silicon substitution, and the silicon substitution for the antimony also increases the lithium content. And this is the main point. So we can see that anion disorder does not play any role whatsoever. It really is the lithium content that is affecting things. We're getting conductivities upwards of easily 20 millisiemens per centimeter, either for annealed, 15 to 20 for annealed versus sintered pellets. So these are superionic conductors. And the reason for that is, the reason for that is shown in this overhead, where effectively in the pure antimony and diodide, we have 2 lithium sites, whereas in the silicon substituted material, we have 4 sites. And we introduced 2 additional sites in the 48H and the so-called 4D site, and again, very little anion disorder. So one of these sites actually sits in the intercage transport pathway, and it provides a metastable site for ion diffusion. And this is what results in the high conductivity. So anion disorder in the iodide is irrelevant. It really is this new pathway for transport in the intercage regime that we are able to develop by literally stuffing lithium into the structure by virtue of incorporating silicon. So we go from a lithium poor regime to a lithium rich regime. And so Yifei Mo has shown that when you stuff lithium into a structure, you effectively populate these high energy sites, and that activates concerted ion migration, lowers the activation energy for diffusion. And we believe that this is the mechanism that's responsible for our conductivities of upwards of 15 to 20 millisiemens per centimeter. So I'll just end off. Well, I was going to end off with a slide of spinel, but that's missing from my overhead. So instead, I'll just, my time is almost up. So I'll end up reminding, everyone of the sponsors for our work. This is mostly done partly by NSERC. BASF sponsored our antimonide Argyrodite work. And I want to say once again, happy birthday, 98th birthday, John. You've been a true inspiration to me for so long. It's in many different areas. And so solid state batteries are just one of them. And so I'd like to thank all of the people that contributed to the work, and thank you for your attention.
Okay, thank Professor Nazar for your interesting talk. I mean, in solid-state lithium-sulfur batteries. We have collected several questions. The first question is, what is the expected energy density in solid-state lithium-sulfur battery as compared with the traditional liquid lithium-sulfur batteries?
Yeah. Well, I think it's a little too early to start judging on energy density, simply because it really depends on the type of electrolytes that you bring into the system and how much sulfur you can really incorporate. So what we really need to do in order to increase the energy density of the system is to move above where we are now, which is about 35% sulfur. But we're also using the vanadium, the VS2 as a capacity increase. So we would like to incorporate more sulfur into the system, upwards of about 60%, and then I think we can start talking about practical energy density. And that's going to require the use of the binders and more complex architectures. So I would like to hold off on predictions of energy density at this point until we sort of move to the next step.
Okay, thank you. So the second one is, what is the future, for lithium-sulfur battery? Is a solid-state lithium-sulfur battery or the traditional, the liquid sulfur batteries?
Well, always the difficult questions. I personally think that the future is probably in solid state, or what I would call quasi-solid state. The jury is still out. I think we've been all fighting with the problem of dissolution reprecipitation in cells, trying to really, there's been so many different approaches to this that have, to a large extent worked, but a large extent still have a long way to go, that I think it's time to turn our attention to different ideas. And so this is, again, you've asked, it's sort of an opinion here as opposed to an absolute proclamation, but I think that quasi-solid state is probably going to have a lot of advantages in controlling that dissolution precipitation. And it's pretty clear that we can undergo the solid state conversion fairly readily. So it's a matter of finding the right, as I said, architecture and so-called ingredients to really facilitate that conversion. And I think that will probably overcome, I think that will supersede the traditional liquids itself.
Okay, thank you. Because there are many questions, maybe I will transfer to you by email. Thank you again for your talk.
Thank you.
Thank you. So now the last